Greetings and welcome, friends, boys and girls. Welcome back from the Stone Age, and welcome to, I don't know, Greek geometry. That's all right. Don't worry. That's fine. That's just for us. It's an inside joke, is what it's called. You guys will tweet about it. You'll add in the comments like, I know what he's talking about, but no one else will. Today we're talking about areas of polygons, and the majority of this lesson is going to be about areas of regular polygons, which, in case you don't remember, a regular polygon has all congruent sides and angles, which none of these shapes that I have on the screen right now are regular, although the one on the left, that diamond shape, that rhombus, is an equilateral shape. It is not equiangular, so it is not regular. But check this out. If I take the two diagonals, D1 and D2 of this rhombus, all right, you guys imagine that? You with me there? Right? Anthony, you too? And I wanted to find the area of this. The base of the triangle that half of this rhombus would be D1. You guys agree? You tracking? Yeah? And the height of this triangle would be half of diagonal 2, right? You guys with me? So half of diagonal 2 is the height. The area of the triangle would then be 1/2. This is the part that they should have written. Area of the triangle portion would have been half the base times the height. And the height is 1/2 D2, right? And what's a half times a half? A fourth. It's all right. Don't worry. A fourth. So the area of this top triangle is 1/4 D1 D2. So what would the area of the entire rhombus be? It would be twice this number, right? Because do you guys believe these two triangles are congruent to each other? Because reflexive property for that diagonal is congruent to itself. Side, side, side. Man, do you remember those days? You miss it. Those were the easy days? But we used to hate proofs. So if I double the area of this triangle, 2 times a fourth, D1, D2, notice 2 times a fourth becomes a half, and I get 1/2 D1, D2 is the area of the rhombus, right? And that is the area for that. Turns out some very similar outcome works for a kite as well. All right, so here we go. Here's 2 area formulas. I don't think you guys see these in middle school, to my knowledge. But these are the area of a rhombus and kite. So not as complicated as it looked like a second ago. Do you guys agree? Right? Like you guys were like, whoa, because there was all sorts of crazy stuff. But it's actually an easy formula. You just half D1, D2. So let's do one of these little problemas for us, shall we? I would agree. They would both have the same type of what's called, oh, wait. No, I can't think of the guy's name. Starts with an S. Skinner, no. I can't remember. The pattern is specified complexity is the issue, whereas a snowflake is a reducible pattern that the amount of information taken to describe a snowflake could be done in a very pattern fractal type equation, and so the amount of specified information to describe a snowflake is less than the specified information contained in a DNA or a portion of a DNA molecule, let's say like a RNA molecule that contained the same atoms as a snowflake. Transfer RNA? Yeah. So anyways, find the area of each rhombus and kite. So the area here is, guys, you guessed it, half the diagonal times the diagonal. Do I have to distribute this 1/2 to both of those? No, definitely not. Super illegal because you don't distribute multiplication over multiplication. You only distribute over addition or subtraction. So half of 6 is 3, and 3 times 8 is 24. And area is measured in square units. So this is in meters squared, right? Right. And No, because multiplication is commutative. You can change the order in which you multiply, whichever happens to be more convenient for you at the time. So let's see, half. These are both the diagonals by the looks of it. Be careful. Sometimes these problems might give you something like one of these heights or something, and then, or maybe even you have to, what if I even gave you like that dimension, and then you have to use Pythagorean theorem in reverse. They'll try to trick you or something, but actually I'm going to do half times the 10. Well, I just had a glitch happen there. Glitch in the matrix there. Half of 10 is 5 times 7. That's 35, if my elementary school teachers taught me right. A 35 centimeters squared. Which, what do we call centimeters squared or square centimeters? Squentimeters. Right? Yeah. Squentimeters. We got to get that trend started. Okay. What's up? What's up? Yes. However, the two odd numbers multiplied will still not ever become even. But yes. Yeah. Right. You could put the 2 in the denominator and you'd multiply the two odd numbers. Yeah. Because the way these triangles, the top half triangle here, the area of the top half triangle is still going to be half the base times the height, which this base is this diagonal, and this height is going to be half of that diagonal. So that behaves the same in both of those figures. Good question. Good question. All right. A little bit more complicated. Here's some terminology for you. Finding angle measures in regular polygons. Let's see, the diagram shows a regular polygon inscribed in a circle. The center of the regular polygon and the radius of the regular polygon are the same as the center and radius of the circle. So, center of a regular polygon, you guys probably could have guessed, but the radius of the regular polygon is going to go to one of the vertices of that shape, or any vertex of that shape, and all the radii are going to be congruent to each other. Okay, so the radius of a regular polygon. Question, is the radius longer or shorter than this orange segment? Longer, right? Because it's the hypotenuse of this little right triangle, it's going to be longer. So the radius of a regular polygon is the distance from it's the segment that goes from the center to the vertex, because that's the furthest point out. The apothem, however, will be the shortest distance from the center to a point on the regular polygon. That's right, apothem. Although I was talking to some of my math buddies earlier, and because math is typically a written language, it's not always verbalized, we were kind of like, we were wondering, I think I've heard people say apothem, but I'm a fan of apothem. Yeah. Yeah, who knows? Maybe it was lost to like generations of, because it was written first and not verbally spoken, and we don't have recordings. Who knows? But apothem is how I say it, like the animal opossum. And the apothem is the distance that goes from the center to the midpoint of the side. Okay, so it goes to the midpoint. You could actually even say it's a perpendicular bisector, because it is a perpendicular bisector. So that's the apothem. We're going to use that today. And the word, here we go. The word apothem refers to a segment as well as a length. Huh, cool. For a given regular polygon, think of an apothem as a segment and the apothem as a length. Yeah, it's both. Yeah, the apothem is 3, I could say. All right. And the central angle of a regular polygon is the angle formed by 2 radii. So that is called a central angle, not unlike the central angles that we had with circles. All right? And I can find the measure of a central angle of a regular polygon. This is valuable. Take 360 degrees divided by n, the number of sides. That will equal the measure of a central angle. Right? You guys buy that? That makes sense, right? You with me? All right, so let's see how far we can get today. I'm going to try to snapshot this all in one go. I think I can do it. Yeah. Yeah, I'll go back. Yep. Arc MN. This, not necessarily, you're thinking about like radians, and if I was to wrap the radius around the arc. The only reason they have the circle here today is just so we understand the concept of the center and the radius as being the same in the polygon as the circle. Radii is plural for radiuses. No, radian was that idea, which you're not even going to ever see again until pre-calculus days, which it's super helpful as a means of measure. But here we go. All right, find the angle measures in a regular polygon. All right, let's find, so here is an inscribed regular pentagon, and it says find each angle measure of angle AFB. All right, right there. So there's 5 sides. Let's have you guys calculate that. Yep. We're going to look at those course pacing as well, again, and try to talk about... kind of look. Okay. Yep. All right, so guys, how many sides does a pentagon have? N equals 5. So the measure of AFB, is this a central angle? Yes, because it's composed of 2 sides, which are radii. And so I'm going to do 360 divided by 5. Check out how I do this. I would do 360 divided by 10, which is 36, and then double it, right? That's how I do that math in my head. 72 degrees is the measure of a central angle. About AFG, which would be like half of that angle. You guys agree? So that's going to be 36 degrees. Let's actually write that work out. 1/2 of 72. So 36 degrees. Right. Box it. And Gaff, not to be confused with old Gaffer who lived in the Shire. GAF. Ooh, how could I find that angle? NeoGAF, I think, is like an internet, like... I do not know. There you go. And now that's the only thing you remember after you had a gaff drop on your head? Fine dining and breathing. How about GAF? How could I find this angle here? Ish. Okay, if you're thinking about the radii triangle. Yep. I was looking at in terms of the fact that these are 2 acute angles in a right triangle, so it's going to be complementary to this angle and 90 minus 36. But yeah, there are multiple ways that you could find that. 90 minus 36, what's that going to be? Like 54. I wasn't even close. All right, let's get to one of these more interesting problems. Here we go. No, but I got to get to like these beast mode problems. All right. Now, the way we're going to find the areas of regular polygons, check this out. It's going to be related to the apothem. It's going to be related to the central angle, all of these different things. Is this. I'm going to find the area of one of the triangles in whatever my regular polygon is. Okay? So these dimensions would be R. This is the apothem, right, labeled A. This would be S, the side length of that polygon. We good so far with that terminology? All right. If I want to find the area, I could find the area of this triangle, which would be half the base, which is S, multiplied by the height, which is A. All right? That's the area of that triangle, and I would then multiply by the number of triangles that are in this, and that would give me the area of the whole thing. General concept, good? Good. Now, it turns out that if I was to use the commutative property here and change the location of this S, I could do n times S first. And n times s, the number of sides multiplied by the length of a side, is going to give you the perimeter. And that's what the P represents. So the area of a regular polygon will be half the apothem multiplied by the perimeter of the polygon. Yeah, yep, lowercase a is apothem. All right, I like to call this formula half ap. Yeah. Yeah? No? We're good? Now, the challenge is going to be that the way the information is given to you will sometimes require you to do some trigonometry. That's right, sine, cosine, and tangent are coming back, friends. So if I gave you a radius and you needed to find the apothem and you knew this angle or you knew the central angle, you could find half the central angle and then be able to use, right, cosine is adjacent over hypotenuse, right? You might end up having to use some of your old school tricks to figure this out, okay? Let's see what we can do with example 3 here. See how far I can get. I'll at least get it set up here. Oh, perfect. Perfect. Eventually. I can't guarantee its safety. What if like you brought your textbook back and then I hid it on purpose and then charged you for it later and then I sold it personally on the internet to make some money for my Hearthstone cards? I kind of like my plan better, buying Hearthstone cards. But anyways, finding the area of a regular polygon. A regular nonagon, how many sides? None. Oh, I like it. N is equal to 9, is inscribed in a circle with a radius of 4 units. Find the area of the regular nonagon. Let's first figure out the measure of a central angle. So that's going to be 360 divided by 9. And Tyler, did you already calculate that? Oh, okay. You said 4 something. And I believe 9 goes into 36 4 times, and then multiplied by 10 is 40. 40-degree central angle. So if this entire angle is 40 for one of these right triangles, this angle is going to be what? 20 degrees. So let me blow this up. All right, so here is the radius, here's the apothem, here's the right triangle, right? I am going to need to find this dimension, which is going to be half of S, right? Because the entire side length is right here. I'm going to need to find the apothem, and I'll be able to, using those things, figure out the area of the entire thing. Now, I know this is 20 degrees, so let's at least get the setup done before the bell rings. To find the adjacent, when I know the radius is 4, I'm going to use adjacent and hypotenuse, that's cosine. So I'm going to say cosine of 20 degrees is equal to a over 4. I'm going to say, to find this dimension, sine of 20 degrees is equal to a half s over 4. Right? Because sine is the opposite to the hypotenuse. You guys with me? All right, so over here, I'm going to get a is equal to 4 times cosine 20. And you guys could estimate that. And over here, I can multiply both sides by 4 and then by 2. This is the same as, I'll just write this as s over 8. Multiply both sides by 8. S will equal 8 sine 20. And I'll find out the S length. And then, how do I find the perimeter? Perimeter is equal to the number of sides multiplied by the length of a side. So for us, that's going to end up being 9 times whatever S is. And I'll use A equals half ap. So the tricky part for us is going to be remembering how to do our trig work. I'm going to keep doing that. When the bell rings, you guys can head out. But I'm going to figure this out for our video. I left my calculator over. Wow. So 4 times cosine 20 is 3.759. You could, yeah. Yep. No. Let's see, 8 times sine 20. And I get 2.736. And so I'm going to end up getting the area is equal to half the apothem, 3.759, multiplied by the perimeter, which is the number of sides, 9, multiplied by the side length, 2.736. And if I multiply all of this out, I should get approximately, I believe, 46.3 units squared, like so. All right, thanks for watching, internet friends. Have a great day. Bye-bye.